Welcome back to Physics 272. I feel that way. Okay. All right. So last time we calculated the electric field of a ring and of a disk. And we did this in the usual way, right? We pretended that the ring was a bunch of point charges. And then for every little point charge, we calculated the electric field at our observation point. By symmetry, we threw away the components that were going to sum to 0, so we didn't have to calculate them. And then we did some calculus. Thank you, Mr. Newton. We did some calculus, and then we found out these equations. So we got the electric field of a ring along its axis. Now, I haven't put the direction here, but you can figure out the direction, right? If it's a positively charged ring, then the electric field should point away. If it's a negatively charged ring, then the electric field should point toward the ring. And we did the same thing for the disk. For the disk, you can either think about adding up the concentric rings, which is one way to do the calculation. I found it a little easier to start from scratch and go from point charges, but you can do whichever makes more sense to you. And in this case, we got a more complicated looking equation, but still pretty similar, that it points away from the disk if it's a positive charge, and it points towards the disk if it's a negative charge. Then, having built these guys up, we took the size of the disk to infinity. So we let the radius of the disk go infinite, but we did it in a particular way, right? We let the radius go to infinity, we let the charge go to infinity, but the charge per unit area we held constant. And then we got that for the infinite plane, the electric field coming off of an infinite plane is uniform, okay? So it's uniform in that it's got the same magnitude everywhere in space, and it always points away from the plane if it's a positive charge and towards the plane if it's a negative charge, where sigma here is charge per unit area. So anywhere I look on this plane, if I take a little chunk out of it and measure the charge on that piece and then divide by the area of that piece, I get the same number, charge per unit area. And this was a bit weird that the electric field comes off and just goes with no abatement, right? So as far away as you'd like to be from that infinite plane, you still get the same electric field. That's weird. We hadn't encountered that yet, where there was an object that we could get arbitrarily far from and still feel the same electric field. So that's weird. But it's because there's an infinity involved. There's an infinitely large there's an infinitely large sheet charge, a plane of charge right there. So one of the other things to think about is how the electric field, how the arrows point in space. So for a point charge, we had the electric field coming off the point charge, and the arrows kind of come out like a dandelion or a starburst shape. And then as the arrows get farther apart from each other, the electric field gets weaker and weaker, okay? For this plane of charge, as the electric field is coming away from the plane of charge, the electric field is just coming straight away, okay? And the only direction you can go away from an infinite plane is straight away, right? It doesn't splay like the point charge's electric field does. So it just goes straight away. And because it's going straight away, there's always the same density of field lines any distance away. So that's intuitively why this electric field doesn't decrease as you get away from the plane. It's a weird result, okay? But it's a true result. Do you have any questions about how that stuff went? Okay? And then we saw that if we add up two infinite planes next to each other, one with positive charge and one with negative charge, then in between the electric fields add, because the arrows are pointing in the same direction. It points away from the positively charged plane and towards the negatively charged plane. And so that was a reinforcement effect. We got twice the field inside. And then outside, the fields canceled completely, so that there's zero electric field outside of two parallel, oppositely charged infinite planes. Now, this is actually a bit like a capacitor. A capacitor has two plates that are oppositely charged, and if the plates are large compared to the distance between the plates, then inside you can pretend you have infinite plates. And so inside, the electric field is about sigma over epsilon. And outside, the electric field is very small. In a real capacitor, there'll be a little bit of electric field leaking out. We call that the fringe field, but it's pretty small, okay? Do you have any questions about that application? Okay? All right. Now, I want to give you some guidance as to how to approximate. We've done some situations where we make approximations, such as the infinite plane, or getting close to a disk, or close to a rod, or far from a rod. So I want to give you some guidance as to how you know when a particular approximate formula is a good thing to use. When should you use it? When should you not use it? And in all these cases, we have two length scales in the problem. When you have two length scales in the problem, Then you can compare the two, and if one is significantly larger than the other, then it's a good time to think about making an approximation, okay? So, for example, if I have a point charge, and I'm a particular distance from a point charge, the only length scale, the only distance in the problem is how far am I from the point charge, because the point charge is 0 extent. It doesn't have a length of its own. Now, if I have the case of a rod, or a disk, or a sphere, something like that, now I'll have two length scales in the problem. I'll have how far away am I from the object, that's one length scale, and then I'll have how big is that object, that's the other length scale. So anytime there are two length scales, think about whether you can make an approximation. And the way to make it just be crystal clear is to pretend the length scales are money, okay? Just convert into new units where it's money. And then think about having one length scale represent billions of dollars and the other one represent pennies, right? If you have two friends and one owes you $1 billion and the other owes you pennies, who do you go after, right? You go after the person who owes you $1 billion, and then once you have your $1 billion, do you even care to go collect 2 pennies from your friend who owes you hopefully you don't. Come on, I don't care. What do I care? I'm a billionaire. Here, have some extra pennies, right? You don't care. Okay, so if you see this situation where you're going to add together something that's like billions of dollars and add pennies to that, don't even bother with the pennies, right? If you were a billionaire, I guarantee in your checkbook when you do I don't even know if you do that anymore, if things online. But anyway, when you keep register of things, you wouldn't even bother keeping track of pennies. So when to approximate, let's say, for example, we have a rod. So let's have that, we've already calculated the electric field of a finite rod, and the rod has a length to it, particular length, and then I'm going to be a particular distance from the rod. Now I have two length scales in the problem, the size of the rod and how far away am I from the rod. So when I have two length scales, I should think, can I approximate here? So let's say that we have a rod of 100 meters in length, and I'm going to be a distance of 1 millimeter away. Already my diagram is not to scale, right? If I'd drawn it to scale, you wouldn't even see the separation between the rod and the point, okay? So always do that. Always draw a diagram and then think about, well, what is the ratio of these lengths here? Now in this case, the distance from the rod, x, over the length of the rod, those two length scales, the ratio of them is very small. So 10 to the minus 5, that's much less than 0.1%. That's my cutoff for these things. If the ratio of your lengths is 0.1% or less, think about doing an approximation. It's a good time to do that. So here's the full equation, the exact expression for the electric field coming off of a rod, if you're in the bisecting plane of the rod. And I can see that I have an expression inside of this, I have an x squared plus an L over 2 squared. That's what you're looking for. You're looking for the plus sign. So find the plus sign somewhere. If there's two different length scales on each side of the plus sign, and one is wildly larger, think about making an approximation. And here's how you do it. Pretend they're money, okay? Pretend they're money. One's billions of dollars and one's pennies, right? And this guy screams, show me the money. In my example, where's the money? Where's the billions? It's on the L. The billions is on the L. So if the billions is on the L, that's where the money is. Don't care, right? This guy's like billions of dollars. This guy's like pennies. Who cares about pennies? What's a few pennies among us billionaires, right? We don't care. Wouldn't that be nice? So you just X it off, right? Who cares about the pennies? Because I'm adding pennies to billions, right? So X it off. Now can finish your math, having taken care of that term. So these were added together. I crossed off the really small term, and then I write down the math neglecting that really small term, and then I continue on. Okay? And that's how you make these approximations. You need to find two terms added together where one is like billions of dollars and the other is like pennies. You X off the pennies. Question?
So why do you get rid of that X and not the other one?
Oh, excellent question. So he wants to know why, when I went back here, why did I focus in on this X? Why don't I cross off X everywhere? So I can only cross things off when I have two things added together. So the two things added together, 1 billion plus pennies is still about 1 billion. But some number times pennies is going to reduce the whole thing. So that's a good question. I do look in the expression for the plus sign. So there's the plus sign. It could be a minus sign sometimes, but look for the addition term. And look on either side of that. If one's really small, just neglect it. Okay? But you're right. I can't just neglect the X everywhere. Yeah. Good question. All right. Other thoughts about this? I hope this gives you some guidance as to, we're kind of trying to train you in the homework as to when you can make a good approximation and when you shouldn't make an approximation. So if you have a situation with two length scales and one is wildly larger than the other, look at your expression, your exact expression, and see if you can make an approximation. And this is how you do it. You find the plus or minus sign, you neglect the side that's pennies, cross it off, carry the math through, and then that gives you the approximate expression. And it also tells you when it's OK to make that approximation. Okay. Any other questions or comments about that? OK. All right, so new material for today, we're going to look at spheres. We're all about spheres today. We've done a rod, a disk, a ring. We're going to do spheres now. And we'll see that we'll have a hollow sphere of charge, and we'll see what the electric field is for that. And then we'll have a solid sphere of charge, and we'll see what the electric field is for that. In the hollow sphere case, we're going to assume that I simply have a spherical shell, and there's charge uniformly distributed all over the surface of the shell. In the solid sphere case, I'll assume I have the same charge, but I'm going to uniformly distribute it all through the interior of the sphere. So in both cases, it's helpful to think of these things as being insulators. So the general procedure that we've been using is to cut that charge distribution up into little point charges, and then we calculate the electric field due to one point charge. Then we sum up all the point charges, and as we do that, we sum up all the electric fields, take an integral, and then we get an answer. Okay? And that's, of course, a valid way to do this. And I could show you all that math, but you've seen it a few times. Plus, in this case, it's actually really hard. So it's more work than we want to show you in lecture. So we're going to take the other method, which is, since it's a lot more work, we're going to use symmetry, skip the actual calculation, although it does work out. And it gets to be a bit like this cartoon here. I think you should be a little more explicit here in step 2. There's the magical step, then a miracle occurs. So for now, you'll just have to say, look, if we actually did all the math, it would formally come to 0. All right? Later on in the class, we'll learn a really nice trick called Gauss's law that will let us prove it for real in a much quicker way. So we'll do that then. All right. So let's think about then using symmetry. We'll go back to symmetry principles and think about what is the symmetry of a sphere. So one of the things we need to think about is the electric field should have some sort of shape to it that is coming from the shape of the sphere itself. So watch this. I'm going to rotate. Here's a sphere. Okay? I'm going to rotate it. All right, are you ready? Go. Did you see it? Okay, I rotated a sphere, and it looked just like a sphere, right? And then I rotated the sphere, and it looked just like a sphere. Here's the nice thing about when we take the physics and turn it into math, okay? When you translate it into math, if there's no difference in your diagram, if you can't see the difference when you rotate the thing, the math can't tell the difference either. So in physics, if you can't tell the difference, there is no difference, okay? So if I rotate this sphere, it's the same physical situation as the original sphere. Right? That means the electric field is going to have that kind of shape, such that when I rotate the electric field, it looks the same as if I hadn't rotated it. Now, another thing we need to take into account is that from very far away, every charged object looks like a point charge. Okay? So if I take that sphere and move it very far away from us into the next building, it's still there, but from very far from the sphere, it looks exactly like a point charge. So far enough away, we need to recover the point charge equation for the electric field. Okay? And whatever it is up close, it needs to also have that symmetry of the sphere such that when I rotate it, it looks the same. So we'll combine these two ideas, that the electric field has the same symmetries as the sphere, that it simply has to be some sort of radial distribution. It can point out of the sphere, it can point towards the sphere, but it can't point sideways, because if it pointed sideways, I'd be able to tell if I rotated the sphere, right? But if it points towards you and I rotate the sphere, now there's another piece pointing towards you, that sort of thing. So it's got to look like a point charge from far away. It has to look the same if I rotate the sphere. And so this is the solution that does that. Basically, outside of the spherical shell, the electric field takes the same form as the point charge. And it just always looks like the point charge. Even if you're really up close, it still looks like the point charge. Okay? You had a question already. Did I answer the question? No, you got it? Okay. All right. So the electric field has the same symmetries as the sphere, and the result is that outside of the sphere, the electric field looks as though there were a point charge sitting smack in the middle. Any questions or comments or complaints about that? Okay. So here's the question. Question is, a charged sphere with charge q sits a distance d from a point charge. Okay, assume this sphere is insulating, by the way. Is the force that the point charge q exerts on the sphere the same as the force that that point charge would exert on another point charge big Q? So this little charge is exerting a force on the sphere. How does that force compare to if I didn't have the sphere, but I had a point charge of big Q sitting at the center? OK, what are some things we need to consider in order to solve this problem? What are you thinking? Or you can always tell me what your neighbor is thinking. And then maybe your neighbor won't talk to you next time. That's OK. All right. So what's either an answer or a line of reasoning that we should draw out and think about? Yes, please. OK, so I'll just repeat it for people in the back. You chose yes because the electric field of this sphere is identical to that of a point charge. So in some sense, this should be identical to that. OK, yeah, please, right here. OK, all right, so I'll repeat that for people in the back. So you said, look, I didn't give you a length scale. I just said it's outside. It's some distance, and it's outside. So then I can take the limit where they're really far apart. And then the limit where they're really far apart, it's really clear that the sphere looks just like a point charge. So they must be the same. Yeah, it's always good to think about those limits, actually. I think that really clarifies things a lot. Right? You come up with an answer, and then you think about it in an extreme limit, and you see if your answer is robust against those extreme limits. I think it really clarifies things. Yeah. Good. Other things we should take into account? OK. What about, OK, so far we've discussed what the electric field is at Q, at the little point charge Q, right? But really, we want the force on the sphere. Don't I need the electric field at the sphere in order to calculate that force? Kinda. So I think you used another principle to finish the problem. Because so far we're thinking in terms of the electric field that the sphere puts out and what it looks like at the point charge Q. And that gives me the force that the sphere exerts on the point charge. But we want the other direction. Yeah? OK, reciprocity. So we know somehow, whatever this is, it's got to be equal and opposite forces. So yeah, we put that principle in as well, so that if I know what the force is on the point charge, it must be equal and opposite of the force on the sphere. Yep. Good. OK, I think we drew out all the physics. Is there something else we should think about? OK. All right. So inside the spherical shell, this is the magical step that I'm not proving to you. But the answer is that inside of a spherical shell, as long as this is an insulating spherical shell and the charge is uniformly distributed and can't move, then the electric field that this sphere puts inside of itself is net zero. Okay? So all the little charges contribute something, right? Each charge contributes some electric field inside. But if I sum up all the electric field vectors, so just thinking, for example, at this spot B inside the sphere, there is some influence at it due to this point charge here, number 1. It's actually pretty big since B is close to 1. And so there's an electric field pointing to the left there from charge 1. From charge number 4, there's an electric field pointing to the right. It's a little weaker. So those don't quite cancel. From point charge 2, there's an electric field down. From point charge 6, there's an electric field up. Those cancel. And then from this whole side of the sphere, there's a bunch of vectors pointing to the right. From this whole side of the sphere, there's a bunch of vectors pointing to the left. It's a complicated summation, but in fact, it all sums up to 0 in the end. So inside the electric field, inside the sphere, the net electric field due to all those contributions sums up to be 0. And it's a long calculation that I'm just not showing you the guts of, and instead I'm saying then a miracle occurs. All right? And later when we use Gauss's law, we'll be able to see exactly why that's the case with a much shorter calculation. Okay? So for now, what I want you to know is the result, that inside the spherical shell, the electric field is 0. So it means if I were measuring electric field and I were outside the sphere measuring electric field, I would detect something. If I'm inside the sphere measuring, let's say I'm inside and I don't see the shell, and I'm trying to detect whether it's there just by measuring electric field, I wouldn't know. Okay? It's as though that shell is invisible to me. All right, so here's the summary for that. The electric field of an insulating spherical shell from the outside for an observation point little r larger than the radius of the sphere, it looks just like a point charge located at the center. If I'm inside, if my observation point little r is inside the sphere, it looks like 0. Question?
What does it equal on the surface?
Okay, so on the surface itself, let's not consider on the surface itself. Okay, let's have some really sharp boundary to where we can say that we're either outside or inside, and we'll let the surface itself be just a boundary. Okay, I see you are a math major, or could have been. Okay, all right. Okay, so we'll just, that boundary right there, we're going to either say you're outside or inside, that it's so thin you can't sit right on it. Okay, and that's kind of a physicist way to answer that question. A mathematician would answer it a little bit differently. Okay, right. Actually, really you can choose it either way you like. There's only one point there, right? As a function of distance, there's just one point. And so you'll get the right physics answers either way you want to look at it. If you want to look at that point being 0, you'll get the right answers for everything. If you want to look at it as connecting to the outer one, it's OK. Yeah, because, well, you know, from the outside, it's all going to look the same. Or from the inside, it'll all look the same. Yeah. Good question. All right. So inside the insulating spherical shell, let's just think through the physics consequences of that. Okay? So the physics consequences of this is, let's think of an insulating spherical shell. So I'm not going to let that charge move around. Now I want to put a charge inside. I'm just going to take an extra charge and put it inside. Okay? What's the net electric field inside of the sphere now? Okay, there's a negative charge there. So the negative charge is putting out an electric field. So there must be something there now. So the negative charge exerts its electric field, which adds to the 0 contributed by the sphere. Yeah, right here?
Isn't it still 0 because the positive charges would rearrange themselves to make the net electric field inside 0?
OK, all right. So he's bringing up the point of, well, what if we had a conductor? If I had a conductor, if the spherical shell was a conductor, then the charges could move around, and I'd have to think about, you know, that'd be a different situation, right? You're right. So we're going to make this guy, for now, we're going to ask your question in like 2 seconds. So for now, I want to keep this guy insulating. And if the spherical shell is insulating, then the charges don't run around on it. They just stick wherever I put them, and they'll be there. Yes, but keep that in mind, because it's exactly where I want to head. So for now, with an insulating spherical shell, there is an electric field in there. It's due to the point charge. What's the force, though, on the negative charge? What's the net force on that guy? What is it?
0.
0, OK, and why is it 0? Yeah?
All these forces cancel out.
Yeah, OK, so I can think about it either in terms of, OK, there's all these forces on it from all the charges out there, but they must cancel out because the electric field at that position canceled out, at least due to the sphere. So the point charge doesn't exert a force on itself. We just care about all the other fields. And so the fields that are produced external to itself, the fields that are produced by the sphere, all come to 0 field, so then there can be 0 force on it. So that's kind of weird. I can put a point charge anywhere inside of an insulating charged sphere, and as long as that insulating charged sphere has its charge distribution uniformly distributed, there'll be no effect. I can just put the charge there, and it won't move. Okay? Now, what if we think about the case where the sphere is conducting? This is the question you brought up in the back, OK? All right, so now we'll make it a little more complicated. Now I have a conducting sphere. I put charge on the conducting sphere. What do these charges that can now move around because it's a conducting sphere, how do those charges respond to the negative charge I put inside? So I've got this little negative charge down here to the right. Which way do you expect those positive charges to move? Yeah, they're going to want to move towards it a little bit. So if I have this guy being a conducting sphere, where the charges can move. If I put a negative charge here, the positive charges will move toward it. They won't all run to the same point because they repel each other too, but there'll be a little net excess positive charge distribution. And then once that happens, now what's the force on this guy? On the point charge. Pardon?
Infinity?
Well, it'll tend to, it'll get attracted, right? So the positive charge is attracted to the negative charge. If positive charge gathers over here, that'll give me a net electric field now inside the sphere, which will then pull that point charge over. So the point charge will be unstable. If it's a point charge inside of an insulating sphere, it won't feel any forces. For the conducting sphere will rearrange itself, and then it'll suck the point charge onto the surface. Okay. Questions about that? Yeah?
What force would the negative charge apply on the sphere, on the shell?
Okay, so you're asking the question of, let's think of the point charge and what influence it exerts on the shell, and what kind of force does it apply. So if the negative charge is inside of an insulating shell, it actually won't be allowed to exert a force.
Okay.
It looks like it should, but you can use reciprocity to tell you that, well, the point charge isn't feeling a force, therefore it's not exerting a force on the sphere. Okay, if it's a conducting one, it's different, right? Yeah, question here. Good thoughts.
The outside of the insulating shell, if there's the negative point charge on the inside.
Oh, okay, that's a good question. So you're taking this one step further. You want to take let me see if I understand. You want to take my setup here, where it's an insulating sphere of charge, put the negative charge in the interior, and now what's the field outside? Is that the question? Well,
I mean, since they're not, I don't know.
okay, no, this is a good question. And so the thing is that in order to find net electric fields, I always need to think in terms of the electric field that the point charge puts out, and it's all over space. Right? Fields don't stop. They just go all over space. Okay? So the point charge is exerting some, starburst-shaped field all over space. The sphere is also exerting, outside of itself, it exerts a starburst-shaped field. Okay? So then outside, I'll get the summation of those two. So I will get something. Yeah, so the point charge still exerts its own field even outside of the sphere, if it's an insulating sphere.
Okay, so you just if you're going to calculate the...
Yeah, exactly. So if I wanted to, yes, so he's talking about how to get the addition. So if I wanted to get the total field out here for this physical configuration that I drew here, I would write down the electric field due to this point charge, and then I would pretend the sphere was a point charge concentrated at its center, write down that electric field and add them up directly. And I'll get a contribution from both. Absolutely. Yep. This is exactly the kind of toy problems that we like you to go through that helps make sure that you understand all the concepts. Yeah, question here. In this configuration, the net electric field inside the sphere would be just that due to the point charge. So it turns out that whenever you have these spherical shell situations, as long as the charge is uniformly distributed all over the shell, as it is in the insulating case, if you're inside the sphere, you may as well neglect the sphere. It's as though that sphere doesn't exist. You can just poof, disappear, have the sphere disappear. Okay? Yep. Good. Okay. Good question. So to clarify this, let's think about two spheres. Okay? So what I'd like to build up to eventually is I'd like to eventually build up to a solid sphere, but for now we're just going to start with two. So let me have two spherical shells, and I have some spherical shell here that's got a charge distributed, make them insulating so the charges can't run around, and then I've surrounded it by another spherical shell that's also insulating and has some sort of charge in it. Okay? Put the same charge on each of them and have them be concentric. So their centers line up. Okay? I have two concentric insulating spherical shells. They each have the same amount of charge on them, Q. Make it positive. Okay, so they each have positive charge Q on them. I'd like you to tell me what's the net electric field in between the spheres. Okay, so tell me what you're thinking. How should we answer this question? How should we think about this? What do we need to take into account? What are some thoughts? Yeah? So you use the fact that this outer sphere is an insulating spherical shell. The charge isn't going to move around on it. The outer sphere is exerting zero field. And since it exerts zero field in its interior. Since I'm at a point that's interior to that sphere, I may as well throw out the outer shell and then answer the question. And then it became clear, and you said, OK, then just the inner shell contributes, and you got B. Yeah? OK, this is good. OK, so, and I like this. We should always think in these various limits. Well, all right, so what if I had really thin spherical shells, and maybe I could go to a limit where this becomes like two infinite planes. I think that's where you're thinking of. And then in that case, I'm going to get contributions from both equally, and then I'll get net zero. That's a really good line of reasoning that I had not considered before. I'm going to think about that. OK, all right. Yes, that's a good point. OK, yes. So let's stick to the sphere equations. And what we know is that if this is an insulating sphere on the outside, its contribution to the electric field interior to itself is zero. So if I'm at an interior point to that sphere, I may as well throw out the outer spheres, really. So wherever I'm standing, any spheres that are external to me, throw them out. Now finish the problem. And now I just get a contribution due to the inner sphere, and that's going to give me answer B. That in this middle region, all I notice, electric field-wise, is the contribution from the inner sphere. So then the answer has to be B. Okay. So we did our two spherical shells. Here's the answer, is that interior to both of them, I get no contribution. In between them, I only see the contribution of the interior sphere. And then outside of them, I see the contribution from both spheres. Okay? Now, if I think then of adding up a bunch of spheres, now I want to build up the net contributions of a spherical ball. Okay, so I'm going to take now the case where it's not a spherical shell, but I want a ball of charge, a whole sphere where the inside has charge inside of it as well. So I'll distribute the charge all throughout the interior, still think of an insulating sphere, and I want to know what's the electric field outside and what's the electric field at various places inside that sphere. So if I think about now what happens if I add up 8 concentric spheres, I'll just get a contribution from all 8 of them if I'm at an observation point outside. Okay? So I want to build up the solid sphere. Let me have a total charge on the solid sphere of total charge big Q. Its total volume is 4/3 pi r cubed. Okay? And then I can also think about, well, what's the charge density? Density is always with respect to either volume or area or linear density. It depends on your problem. In this case, I've uniformly distributed the charge over a volume. So I need to think in terms of charge per volume. So the charge per volume here is the total charge Q divided by the total volume, 4/3 pi r cubed. All right, and all of that was not confusing, I hope. Now, let me think about building up the total volume by summing up all these shells. I want to sum up all the shells. So let's stop at a point midway. Let me say I'm going to make an observation point here at little r. If I'm at little r, then I feel a contribution from that middle sphere. I feel a contribution from the next shell, and the next shell, and the next shell, and the next shell. Okay? All of those shells contribute to an electric field that I can feel at position little r inside. But all these other shells are exterior, and I don't notice the exterior shells. So we just need to figure out, if we can calculate what's the net electric field due to that inner ball, then we know what the answer is. So what if we stop here at little r? Okay, we're going to assume that the charge is distributed uniformly throughout the entire interior of the sphere. So I just need the charge so far, right? If I want the electric field right here, it only depends on the interior spherical shells. How much charge do I have so far? I don't know, but we're going to figure it out. So I'm going to write down the charge so far as delta Q. What's the volume so far? Well, I do know the volume so far. That's 4/3 pi little r cubed. So it's my observation point cubed. So I know the volume so far. Now here's the crux, right? I've uniformly distributed the charge throughout the interior of the sphere. So any chunk I take out of the sphere, let me just take a little chunk out of it. I count the charges on it. And if I also measure the volume and take the charge divided by the volume of that little chunk, it's a number which is the same throughout the sphere. So any chunk I take out, I count the charge, I divide by the volume, I get the same number. Charge per volume is the same anywhere in the sphere. So that means the charge per volume on my inner spheres, right, if I'm just talking about the red contribution so far, the charge per volume is the charge so far divided by the volume so far, right? And whatever that is, it has to equal the total charge divided by the total volume, because charge per volume is the same no matter where I look in the sphere. So that's the key to solving this, is that this charge per volume is the same as the charge so far divided by the volume so far. Do you have a question about that step? I'm just going to say this is equal to that. And even though I didn't know how much the charge was so far, I can now figure it out, right? If this is equal to that, I can figure it out. So here's what we found on the previous slide, that the total charge per total volume is big Q divided by 4/3 pi big R cubed. And what I have so far is the charge so far divided by the volume so far is the same. So now I can solve for delta Q, which is the charge so far. I just take this 4/3 pi little r cubed and move it to the other side. And I get that it's big Q times this ratio of volumes. The 4/3 cancels, the pi cancels, and I'm left with little r cubed divided by big R cubed. And so then the electric field so far, well, from outside of the red spheres, at this observation point little r, the electric field so far just depends on how much charge I have so far. So I put in the equation then for outside of a sphere is 1 over 4 pi epsilon naught. I need the charge so far divided by r squared. And the charge so far was that delta Q. Okay? And delta Q, we said, is big Q times little r cubed divided by big R cubed. And little r cubed divided by r squared gives me a net little r. The 1 over big R cubed stays put. And so this is the solution for inside of a solid sphere. So the electric field inside of a solid sphere has this funny shape, right? My observation point is little r. Big R is the radius of the sphere. And so if I know the total charge on the sphere, then the electric field goes up linearly with my observation point. Because as I go out and out, I'm seeing more and more spheres, right? I step backward and now there's another sphere inside. I step backward and now there's another sphere inside. So the electric field is getting stronger and stronger until when I get to the outside, now it starts to fall off again like 1 over r squared. Okay. So that's the summary then of the solid sphere. Inside the interior of the solid sphere, the electric field goes up like r, your observation point, until you get to the outside, and then it starts falling off like 1 over r squared. Okay? All right, we're done a little bit early today. That's it for today. So I'll see you guys next week.